Welcome to Teradata Pro webinar on Teradata indexing. It is a great pleasure to present to our fans and subscribers for the first time. Why, you may ask, did we decide to launch a webinar at all when we already have so many articles? Well, as you might have experienced yourself, there are thousands of manual pages, pieces of code, questions and answers on forums and blogs for both Teradata itself as well as enthusiasts from all over the world. Oftentimes, when we need to look up a detail, we are happy that all these little pieces are out there. When we explore a new topic for the first time, we are always thankful to have all these manuals from Teradata provided for free. However, we soon realize that one kind of information is typically missing or provided too little, as we think in the world of Teradata. And that is a place or source where you are taught the ideas, where the focus is on your ability to think and work on and with Teradata. You know, it is good to have a large manual from a car manufacturer, but wouldn't it be great, and sometimes even better, to learn how to drive in the first place? We want to break the ground in that direction and contribute our part to the latter. Our training shall enable you to focus on the principles behind a concept while not skipping the technical aspects, see the big picture but grounded in technical knowledge, ask the right questions that direct you towards the root of problems, enable you to analyze real-world problems yourself and draw the right conclusions, independent of where the problems are said to be. This is what Teradata Pro webinars shall provide for you. What are the topics we will cover in this webinar? First, you'll get an introduction into the Teradata architecture. In case you know many of these things, take it as a repetition and as a warm-up. It is important to understand how the Teradata architecture works and is designed in order to understand how indexing works. Then we will provide you with a framework of discussing indexes. We'll go through all the topics and issues of indexing in general, and we will apply this framework to the discussion of one or the other index at great detail, so that you can see what are the advantages, disadvantages, the costs and benefits of a particular index. After having attended this webinar, you will be able to introduce indexing to your work environment, speed up queries, answer tailored as well as standard reports faster, improve the existing indexing landscape, save space, maintenance, and any kind of overhead by redesigning existing indexes, freely and fluently discuss every aspect of indexing with professionals around you, so that you get to the attention of the most skilled coworkers in search for professionals in that field. You might have heard before that Teradata is a shared nothing architecture. This means that each processing unit has its own disk and memory. The processing unit on Teradata is the AMP. AMP stands for Access Module Processor. Each of these AMPs has its own disk assigned. For a normal Teradata system, you can expect to see 4 disks, 2 of which are main disks, 2 are mirror ones. So we have a RAID 0 protection in place. The following architectural cornerstones are important to have in mind for a better understanding of what follows in this course. Take notes if you want, so that you can follow our discussion when we come to the core part. Any data coming in or going out of a Teradata table proceeds through a series of steps, as is delineated here in this slide. First, there is a big rectangle called BINET. AMPs and the parsing engine, PE stands for parsing engine, communicate with each other via this BINET. The BINET consists of 2 very large networks. They are used for simultaneous communication and allow to continue communication over the remaining network if one of them fails. What is the parsing engine? The parsing engine takes over SQL statements, checks them for syntactical correctness and sufficient writes. If these prerequisites are fulfilled, an execution plan is passed on to the next stage. The AMPs are the working units that also take over other tasks like character set conversion, when passing the result sets over to the parsing engine back. In big Teradata systems you can expect to have hundreds of such amps. A key concept related to Teradata is the notion of parallelism. What is that? Parallelism is the even distribution of shares of a table's content over the entire set of amps. And there is a mechanism, part of which is confidential and not to be seen or revealed to the public, we don't know it either, that systematically achieves parallelism as good as it can get with the input and definitions you provide the system with. I've just said that the parsing engine passes along the query and the explain plan. And then what? Well, let's have a look at what happens next. And this is the notion of the hash map and especially the hashing function. Teradata uses a hashing function, which is a kind of translation of one or more values together to one value. The hashing function converts any kind of input to a 32-bit integer value named the row hash value. This row hash is the second kind of output of the parsing engine. It carries all the information necessary to store or retrieve a particular data to and from Teradata. What is input to the row hash? Well, in the usual case of a table with a primary index defined that is made up of one or more columns, it is exactly this set of columns, and for each row, the particular values that make up this primary index. A given set of values always maps to the same row hash, so no matter how often you convert a given set of values, you will always get the same row hash value. The order of the input column combination does not matter. So row hash of A and B is equal to the row hash of B and A. But the row hash of A alone and the row hash of B alone are different values. Therefore, and this is an important first insight that we will come to when we talk about indexes, Teradata can only work with a given primary index if you address it in total. That is, if you provide literals or the right drawing conditions for all of the primary index components. Lacking only one makes a different row hash. The parsing engine, with the row hash value now finished at hand, uses the hash map to derive which amp a particular row shall go. We have represented the hash map in our slide here as a small gray rectangle with numbers attached to it. The hash map is always present on every amp in the amp's memory, the FSG cache. How do we translate from a particular row hash value to the information which amp we shall take and which amp we shall store to? This is done by taking the second half, so the second 16 of the 32 bits of the row hash value. These second 16 bits carry the hash bucket information. You can see here as a sketch in form of a gray matrix. One hash bucket tells which amp number is responsible for the information. In case of a select statement, requesting a row by referring to the primary index in full, we move from the parsing engine, continue with the row hash, turn to the hash map to find the responsible amp, and then request the row to be taken from within the sphere of this one amp. Conceptually, it is the same set of operations whether we have a unique primary index or a non-unique primary index, or one of the indexes using hashing, which we'll talk about later. While it does often happen that queries are not selective enough to be directed to one amp alone, the row storage is an operation that always directs one row to one amp. How can we be not selective enough? For example, by referring to only parts of the columns that make up a primary index. The row hash value, technically speaking, is not the whole story. It is not enough information because several rows with the same key information have the same value, but they shall be stored each. This is what we actually allow for when we define a non-unique primary index. Therefore, further information is needed to be kept. This is where the 32-bit uniqueness value helps us out. The row hash value, together with the uniqueness value, a separate value, allows finally to identify each row uniquely on the disk level. Why is that necessary? Why do we store uniqueness values along with the row hash? It is possible that different primary index columns are mapped to the same row hash. This is a very rare incident. It is called hash collision. And as an insurance against this black swan event, the message to the AMPs to locate a certain row always contains the primary index column value along with the row hash. Locating a row by row hash alone would be sufficient virtually all of the time, but it has to be ensured beyond doubt that any row retrieval is always correct. Now that we understand how primary index hashing works, let us have a look if there's an alternative. Well, traditionally, each and every table had to have a primary index defined. Nowadays, after the introduction of Teradata 13, it is not a must anymore. There are so-called no primary index tables. Let me give you an idea of what happens to the hashing procedure when we lack such a primary index. Due to the functionality of the row hash algorithm, the content of these tables is spread randomly and therefore also quite evenly across all AMPs. Now, that sounds good. We have even distribution by design. Is that really the best solution? Why do we have primary index tables at all? As good as this may sound in the first moment, it poses a threat to performance, because all AMP searches are the only option to work with such NUPI tables. We will soon discover that indexing can help us here. Now that we had a bird's eye view on the architecture, we can step down one level deeper in order to discover what is behind an AMP, what is inside of an AMP, and follow the trail of a row down to the very point of its physical location. This location is the data block, with a standard size of 512 bytes and growing, and uniquely managed by one AMP each, so that there's a sharp divide of responsibility and accessibility. One AMP is responsible for one block, and one block contains rows of one object, one table. Let us now enter the world of a data block. On the right side of this slide, you can see a graphic representation of some of the major elements of the interior of an AMP, namely the master index and the cylinder index. The master index contains the table ID, the cylinder, the lowest row ID, the highest row hash, and the free list. The master index is always present in the AMP's cache. It is always present in the FSG cache, whereas the cylinder index is not necessarily always there and sometimes has to be retrieved from disk. The cylinder index, one level deeper, provides per cylinder the table ID, the sector, the lowest row ID, and the highest row hash, plus again a free list. Those free lists serve to locate and tell where free space is on disk at a glance. The AMP consults these two indexes to find out which way to go with information to retrieve or store. If we follow the flow of data from the parsing engine over to the AMP via the two indexes, master and cylinder, down to one particular spot on the disk, the block, this block, once being identified as relevant, is then moved from disk to the FSG cache. But why is it moved? Because no data on Teradata can be worked with directly on disk. For every read to occur or write, it must first be copied to the memory of an AMP. As you can see, there is typically the highest row hash value in master index and cylinder index included. What happens if we have value ordered indexes? Well, then the master index and cylinder index carry the ranges of a 4-byte integer value instead of row hash ranges. This is a special case. We'll treat this more in detail as we come to value ordering in the indexing section. The core elements that every block is equipped with are the header, that stores the table ID, the row pointer array, and, of course, the data rows. The table ID is the internal identification number behind what you as a user see as a table name. It has to be provided along with the information we mentioned already. The row pointer array holds 4-byte integer values ordered and used for row locating. Rows are stored in a block as they come and under nominal consumption of space. They are unsorted and do not have to be sorted, and they can be rather loosely packed so that intermediate chunks of storage space are left unused. This is a problem called fragmentation. Now, is that really the best solution? Imagine that we imposed a condition that the rows themselves be sorted at any time. Then we would find ourselves trapped in a constant defragmentation activity, and that of course degrades performance by design. Therefore, the only orderly element inside a block is the pointer array. And this pointer array and its orderliness is not affected by any possible row jumble. Data blocks all come in one standard model. It makes no difference if we are to store pieces of a table, an index, or some other comparable element known to Teradata, as at the finest level, the structure, where and how we store is the same. How can we work with the row pointer array to locate rows? The first of two algorithmic approaches is the sequential search. In our simplified block, the light green rectangles represent 9 rows stored in total. The row pointer array consists of 9 elements accordingly. The integer value with which the connection between block and element is drawn is a simple number here. We use white arrows to demonstrate the relationship visually. Our row pointer array is sorted in descending order, starting with a 9 as the first element down to 1. There is some free space in the block, that is, everything that is not light green but dark green in our graphic. With a sequential search, we move from one end of the range of entries to the other in increments of one entry until we have found the entry we are looking for. For, so to say, narrow retrievals of single rows here and there, this algorithm is efficient only if we happen to search the entry at the very end point we start from. Else, it can take many steps until we are done. Nevertheless, a sequential search can be an efficient way of accessing tables if we have to locate each and every row. This is what we do in a select star from query. You might assume now that sequential searches can only be executed over the row pointer arrays with row hash sorting, but a sequential search can be done as well on value ordered data blocks. When we face value ordering, we can limit the sequential search to the range we are interested in, when we do not want to select the table in full. Master index and cylinder index deliver the information which data blocks provide the range of values we are interested in. Once having arrived at the blocks, we can stop scanning as soon as the next value stored is moving outside our selected range. The second algorithm that could apply is the binary search. With a binary search, we always start in the middle of the entire range and determine whether the entry there is equal to, greater than, or less than the value we are looking for. We take the remaining half of the range our searched value must be in and go to the middle entry of that range. We repeat the process and continue to divide, pick appropriate halves of ranges until we have found the entry we are looking for. You may find these kinds of algorithms under the catchword of divide and conquer. Here as well, the search can be done on an array of row hash pointers or over 4-byte integer value ordered pointers. Depending on what we are looking for in a data block, one or the other algorithm can be used, or rather, we may be forced to use the less efficient one, as the majority or even all of the rows of a table qualify for a result set. Furthermore, the chore of finding rows can be of limited scope, so that one emp alone suffices, or we cannot help but search all emps. Let us have a look at each of these situations. What happens when we query a relatively large portion of a table's content, or in such a way that bypasses any indexing? Then Teradata can't help but move over all the table distributions and find out emp by emp which blocks and which rows inside them qualify for retrieval. As we do not come up with individual entry searches inside a block, Teradata has no other option than to move along the line and decide one by one. If the parsing engine has to instruct all emps to search for qualifying rows, and we cannot be specific on which blocks to search for, all blocks have to be copied to FSG cache and scanned for qualifying rows. A full table scan on a base table or a non-unique secondary index subtable is a good example for such a situation. Note that this approach can indeed be called efficient if the task is to touch and retrieve all the rows of a table. We are in this case not better off with a binary search, as this would wildly zigzag around the row pointer array, when in fact a simple sequential search is faster. The sequential search can further be limited to only a range of data blocks if value ordering is established. We call this a range-limited full table scan. If the picture of what we want is a little clearer, meaning that it can be clearly decided which data blocks are relevant, we still may have to work our way through all emps, but this time our effort is reduced at the block level. It may happen that we know quite early which data blocks contain the information we want, but we cannot discriminate over the emps by design of the object we work with. You will recognize what we mean when we come to discussing this element later. Here, in this situation, we are served well with binary search techniques only across the blocks of various emps. For reasons we will explore later, a walk over a non-unique secondary index belongs to exactly this category. Being even more specific about what we need from a table, it can be determined earlier that only one emp needs to be involved. Furthermore, relevant data blocks can be determined clearly, and inside them only this or that row is relevant, so Teradata can clearly apply a binary search. Every direct primary index or unique secondary index access belongs to this category. They are the fastest access methods one can possibly achieve on Teradata. Now that we had a guided tour through the background landscape of a Teradata system, we are equipped with a strong foundation that allows us to understand technical details of indexing and the decisions for or against a particular index better. We can now ask the right questions with respect to the overall composure of an index. But do we know what an index really does by now? Not yet. Therefore, let us advance to the core of this webinar. Whenever you engage in discussing, defining or reshaping indexes in an environment, there are two strategic goals that you want to achieve with indexing. They should be for you what pole star and moon was for sailors in medieval times, a basic orientation and guidance on where you are going with your indexing attempts and whether you are still on track. Note that these two strategic goals also lay the foundation for any quantification or measurement established in order to determine the success of an indexing approach. The first strategic goal is the minimization of I/O. Even in times of SSD disks becoming the norm and ongoing progress in speed and efficiency, back and forth travel between memory and disk comes at a cost. If you can cut this cost while not raising others, why shouldn't we? So one way of reaching this goal of minimized I/O is by selecting fewer rows, by working with an index that will in turn lead to a reduction of costly join preparations. The second strategic goal is an even, or at least more even, distribution of data. If not already achieved by the primary index, other indexes can mitigate the impact of having to refer to tables in ways that simply do not match how they are indexed the primary way. We aim for an avoidance of recurring events of one AMP having to do all the work while the others lay idle, which we generally call skew. If we can make a better use of the entire range of AMPs, why shouldn't we? Let us first separate an alternative attempt to reaching these strategic goals, namely partitioning. Depending on how experienced you are with the various technical aspects of table design, you might be tempted to look for advice on how to partition better or differently in a webinar on indexing. We want to confine our framework to indexing alone and separate partitioning issues from it for reasons that are grounded in architecture, namely, first, index creation leads to the creation of subtables, that is, separate internal objects that lead a life of their own, although of course not completely independent from the base table. Partitioning, on the other hand, is an operation on the base table itself that does not generate objects that are separable from the base table. Instead, partitioning simply reshapes how a base table content is organized and stored. It is a different way of structuring data on disk. Indexing, second, will consume additional space through the creation of subtables. While for partitioning there is some space overhead as well, stemming from the provision for space to store partition affiliation of rows, but it is of a different magnitude. If partitioning is like chaptering a book, indexing is like the introduction of a register at the end of it in order to find personae or topics that are mentioned, and the one or many pages where they are mentioned, aside from what the book is mainly about. Indexing is always related to the creation of separate objects that provide alternative accesses to the otherwise unchanged base table. When you create an index, in the background Teradata creates an index subtable that shares many but not all characteristics of an ordinary table. First, it has a table ID of its own, much like a normal table. This allows the AMP to distinguish the base table and the subtable during data lookup. Second, as it is physical, it consumes space, permanent space. Physical separation between the base table and the subtable also means that base table and subtable are founded on their own data blocks each, and that they will never share a block. A characteristic that is not shared by an indexing object is the principle of distributing the content of a subtable by row hash strictly across all AMPs. We will cover the following indexes, knowing that this is not the full arsenal of Teradata indexing: the unique primary index, the non-unique primary index, the unique secondary index as well as the non-unique secondary index, the hash index, and the single table join index. We do not cover advanced versions of single table join indexes and multi-table join indexes. The reason for the exclusion of the latter one is that multi-table join indexes transgress the sphere of pure indexing and often become more a means to denormalize a data model. Single table join indexes generally stay on this side of the demarcation line between creating alternative accesses to tables, this is what proper indexing is about, and remodeling relationships. One of the many perspectives on indexing is resource consumption. The first aspect of resource consumption is space consumption. The second is the degree and frequency of maintenance involved with indexing. Space usage goes beyond simply watching a subtable consume free permanent space. With large base tables kept manageable in size by compressing on many of its columns, We have to think of what happens if we index over compressed columns. Will the compression then have to be given up for the subtable, or will it be replicated? Next, how does an index consume space not in relation to the size of its subtable, but of how a subtable structure is composed? Then, can we protect indexes much like base tables with fallback protection, and do we have to restate it explicitly for a subtable, or does it happen automatically depending on what the base table setting is? For those of you who cannot recall what fallback protection is, let me help you out here. Fallback protection is a safety measure against hardware damage that causes non-recoverable loss of data by the creation of a second location of storage for every base table row at any time and with any event. With that second store, space need is of course doubled. The second aspect of resource consumption is maintenance cost. Increased I/O activity due to the accompanying activities of every base table content change and the degree to which we can manage or tune it is our main concern regarding this aspect. Which events trigger maintenance? We have to be aware of the many compatibilities or downside effects of indexing with load utilities, like fast load or multiload. Do we have to turn indexing off in this case? What can we do with purely transactional tables in terms of indexing? Fallback protection is of concern to the second aspect as well, because extra protection of table content causes extra activity, typically a doubling of I/O. One characteristic of an index's anatomy is its row distribution. Rows of an index subtable are either distributed by the row hash of whatever is indexed upon, so that they cross the borders of the AMP of the base table row, or they reside AMP local, that is, a subtable row and the base table row, or rows it is pointing to, share the same AMP. With a row hash distribution, the very same general distribution mechanism that landed a particular base table row on an AMP based on its primary index now sends an index table row to an AMP, a different one, based on the row hash of the column values that were chosen to index over. In some cases, it is possible to set a different distribution pattern by the user instead. Can the index table rows be skewed like base table rows, with either unreflected data modeling choices, a clumsy primary index setup, or disadvantageous data demographics in the way, or is it impossible by the very way a particular index is constructed? By coverage, we mean the degree to which an index is carrying all the information needed to fulfill a request, so that index access to the base table is not necessary anymore. If so, we speak of full coverage. We call a situation partial coverage when an index alone cannot answer a query completely, so that the base table has to be engaged to satisfy the remaining conditions. The dividing line here is whether it is advantageous or not to access an indexing subtable in such a situation and finish any remaining row discrimination on the base table, given the pre-selection from the subtable. As an aspect of coverage, we have to find out whether an index is capable of addressing a base table row immediately by its row ID, by making this row ID part of its own composition. Is it further possible for an index to rehash the base table row ID from the information it has ready for use? Put differently, can one derive the row hash of the base table primary index with nothing but the index information at hand? The next key question we can address is how the index data block access takes place. One kind of access pattern is a full table scan. Will an index be used if its usage required a full table scan over the index subtable with a sequential search algorithm then on the data block level? Or will it only be used when a hashed access takes place, be it in the form of a single or an all AMP activity? How are the rows sorted in the data blocks that belong to an index subtable, either by the row ID of the index columns or by a 4-byte integer value of a value-ordered index? Can we combine separate indexes on one base table? There are two ways of combining indexes given we face no limitations. First, several indexes of the same kind over individual columns or small sets of columns can be used together in the execution of a query. A second special case of such a combination is bit mapping. We will explain this method and when it will be used later. Besides combining, we can also stack indexes in some situations. Stacking refers to the definition of an index over one index table at the lower level and a second index definition on the result of level 1. A non-unique secondary index on a single table join index is one such example. A question related to stacking is whether we can define indexes on partitioned tables reusing columns already used for partitioning. There are certain prerequisites that have to be fulfilled by a query in order for the parsing engine to decide to consider an index at all. First, to what extent is an index an all or nothing decision with regard to the match of queried versus indexed columns? Do we have to address the column combination in total, one by one? Does the order matter? When, if at all, is it sufficient to address only a part of the columns, and if so, does it matter which part we address? Second, what comparison operators invoke or prevent index usage, even when there is a perfect match between indexed and referenced columns? What about the like operator, for example, knowing that a value set expressed in the form of a like cannot be hashed? Third, how selective is the index column at all? And how selective is our request over the index column relative to the total set of values indexed over? The difference between the former and the latter is this. Indexing over a gender column on a table with millions of customers is hardly selective, given our customers are not a special population. Querying over an index column that knows thousands of different values, but with a condition that is true for 99% of the population, is a lack of selectivity on the query side, even for a generally highly selective index, for example, one on birth dates or on net asset values of clients of a financial services company open to anyone. Fourth, given implemented optimizer rules may favor the usage of an index or the preference of one index over another when several candidates exist to work with. Rules can be implemented regarding the way indexes are combined or rather sequenced in use. Fifth, statistics alone can righteously invoke the usage or the bypassing of an index, whereas the lack of information on the true demographics can misguide the optimizer to over or underuse an index. Some of the possible statistics one can collect over a base table are mandatory for invoking any index usage, while others can even be redundant and so left uncollected. For some index objects we have to clarify to what extent it suffices to collect statistics over the base table to leave the optimizer well informed on the index object as well. And when do we need to treat an index object as a separate target for statistics collection? Statistics on columns of the base table can be taken over by the index objects in some cases. Some indexes are better suited for a particular database environment and purpose than others, depending on whether the main activities in a data warehouse are loading of data for processing elsewhere, standard operations like reading and changing, or reporting. Some index objects cannot be used for technical reasons, others are not well suited in that what they do good on one side, they cost and degrade on the other for the typical daily activities. On a middle level, that is, within a data warehouse, for one or several tables that closely belong together, indexing is also a matter of the data distribution and velocity. The speed and kind of change that the data undergo over the normal life cycles render some index attempts useless that are done with good intentions, but not good in the face of the maintenance overhead they produce thereafter. Technical limitations refer to the scope of table kinds we can apply a given index on, from ordinary permanent tables to volatile tables and global temporary tables, up to no primary index tables, as well as to the hardwired upper limits of how far we can take it with indexing over one or many tables. Such limitations are imposed for the maximum number of indexes of any kind over one base table, the number of columns we can still combine into one index, the kinds and sizes of data types, and any ordering we wish to implement. A full table scan occurs whenever we do not make reference to the primary index as it is defined, and there is no other index that can be used to qualify a row. Note that these conditions can be fulfilled for a rather slim query as well as for a select star from one. A full table scan is therefore not merely a categorization of the percentage of a table's content we wish to work with, from one row to everything, but rather a matter of how we ask for the rows of a table. Also, take heed that you do not mix up an all-amp scan with a full table scan. While the former is a matter of the degree of evenness of distribution achieved over the content of a table and a matter of addressing the primary index, the latter is related to how the rows shall be located in the data block. When the parsing engine determines that a full table scan is the only option, it instructs all amps to indiscriminately retrieve the content of data blocks of the table via master index and cylinder index into the FSG cache. Only then can a sequential search in every block reveal which of the rows are really looked for given the query conditions. Let us now answer all the questions we discussed in general and in theory for the primary index. First, what about the row distribution? The rows of a primary index are always distributed by the row hash of whatever combination of columns defines the primary index in total. There's no such thing as a value-ordered primary index. If you feel the need for value ordering, you have to either reconsider your data model and what led you to define the primary index in the first place, or outsource that part you wish to sort over in a value ordering form to a single table join index. Skewing is impossible by design for a unique primary index in Teradata. Non-unique primary indexes are skewed to the degree your data are repetitive in the columns you chose for the primary index construction. Take a primary index with high skew as a warning sign. Either something went wrong in your load operations, you have duplicates all over the place, or you should consider changing the data model. Maybe the entity is not so well defined after all. By the very nature of the base table, full coverage is always achieved with the primary index. As the primary index is on the base table itself, all columns of the base table are ready at hand when we use the primary index. With a primary index there is no full table scan anymore, but only hashed accesses. And typically single table amp direct accesses occur. The rows of a primary index are sorted by the row ID of the values that are found in the primary index. The primary index is well suited for being combined with partitioning as well as with any other kind of index. Stacking other indexes on top of a base table with a primary index is not restricted to any type of index. A primary index consumes no additional space beyond what the base table itself does. A downside of including a column in a primary index is that we cannot compress it then, so that we can say the primary index has a shadow cost of space to a certain extent. Fallback protection is available and can be turned on or off if desired. Be aware of the extra ongoing maintenance and space costs you incur with this decision. One prerequisite you should recall by now is that there needs to be a full match of the primary index, composites, and the columns referenced in the query in order for the primary index to be used. Technically speaking, the row hash of the primary index and that of the columns referenced in total in the query have to match. Writing SQL with equality constraints on all primary index components clearly fulfill this condition. The first kind of index we are about to explore now that does lead to the creation of a separate subtable is the unique secondary index. The general procedure of accessing base table rows via a unique secondary index is much like what we described before. Imagine that we select from a table in a way that completely deviates from the primary index, but we happen to have a unique secondary index defined over one of the columns we impose an equality restriction on. Then, the following sequence of events occurs. First, the parsing engine locates the unique secondary index AMP via the hash map. This AMP then locates the unique secondary index block via the master index and cylinder index. The AMP moves the block into FSG cache. In memory, over the block, a binary search takes place. The located block carries the row ID of the base table. Now that it is known which base table row corresponds to the unique secondary index entry, we move back up over the binet, and by the row ID of the base table row, that base table AMP is looked up in the hash map and instructed to retrieve the row. The base table AMP now locates the row via the master index and cylinder index. The base table AMP moves the base table block into the FSG cache, and in memory, a binary search on the base table block takes place to finally locate the row we are interested in. This dual AMP access and binary search is the typical combination resulting from unique secondary index references. By luck, it may be that the AMP of the unique secondary index is also the AMP where the base table row is located, so that the operation is reduced to a one AMP activity. But this is not systematically so, but only happenstance. A unique secondary index subtable is made of, first, a row hash representing the value combination of the index columns, next, the columns over which the index is defined with the original values entered in the cells, and finally, the row ID of the base table row. In blocks filled with unique secondary index entries, the row pointer array contains the sorted NUSI row IDs. Unique secondary index rows are distributed by the row hash of the indexed columns. To the subtable, these are its primary index. Value ordering is not allowed for a unique secondary index, just like it is not feasible for a unique primary index. Skewing cannot occur for a unique secondary index by the very nature of its design. Whenever we add uniqueness to an index, Teradata enforces even distribution across all AMPs. In case of a partial coverage, it is intuitive that a two-step operation takes place. Imagine a query where we select column A and B, while the unique secondary index is on A alone. Then, step 1 retrieves the unique secondary index row, indicating the base table row, and in order to decide on the column B condition, is it fulfilled or not in the base table, we walk from the unique secondary index subtable to the base table for the rows identified in step 1. In case of a full coverage, where our A and B selection matches the unique secondary index that runs over A and B as well. All technical documentation say that there is a dual AMP operation also, while we think it is not intuitive why it must be the case when we select A and B alone, and so are fully satisfied with what the unique secondary index provides, namely A and B. Just take it as a null hypothesis that there is a dual AMP operation until you find one day and can prove that it was not the case for an operation we just delineated. Data blocks are accessed with hash values, and a binary search will take place over the block. Regarding resource consumption, recall that a unique secondary index is a separate permanent table. We therefore need space for column values plus row IDs. We think that it is not the best use of your time to calculate the exact amount of space that will be needed, and, given the effort necessary, a simple trial is often a better approach, given that you are not operating in a database that has almost reached its consumption ceiling. In order for a NUSI usage to be invoked, we have to operate with equality constraints over its components and over all of its components. Strong selectivity of the index is one of the core strengths of a unique secondary index. Therefore, an accurate and recent collection of statistics of the unique secondary index columns is less of a concern as it is for other indexes, because the optimizer derives the fact of row singularity from the very nature of the index anyway. Much of what you know about a unique primary index also holds true for a unique secondary index. The one feature that is truly different is the strong bias for dual AMP accesses and the independence of the spreading of rows of the base table from that of the unique secondary index subtable. The first striking difference in the overall axis pattern of non-unique secondary index lookups is that no hashing takes place to distribute the non-unique secondary index content over the AMPs. The second fundamental difference is that NUSI rows and the corresponding base table rows are always located together on the same AMP. The third difference to a unique secondary index is that one row can reference many and not just one base table row IDs. The typical flow of operations in a non-unique secondary index access is the following. First, it is always an all AMP access, so the parsing engine instructs all AMPs to do a NUSI scan. Each AMP locates the NUSI blocks via master index and cylinder index, moves them to FSG cache, and in this memory a binary search on the NUSI blocks or a full table scan can occur. The usual case is a binary search though. If a non-unique secondary index is not covering our query via the row IDs of the base table rows that are contained in the NUSI, each base table AMP is instructed to retrieve the base table rows as a follow-up. The AMP with the relevant base table fraction locates the base table rows via master index and cylinder index, moves base blocks into FSG, followed by an in-memory binary search on the base table blocks to locate the rows. All base table row IDs are extracted into a spool table, and from this spool table, the lookup of the base table row follows in a second step. A NUSI subtable is made of a row hash of the combination of the index columns, the columns over which the index is defined, with the original values entered in the cells, followed by a list of all row IDs of the base table row that associate with that particular value combination. In blocks filled with NUSI entries, the row pointer array contains the sorted NUSI row IDs, or, if value ordering is in place, a sorted 4-byte integer value. Because of their tie to the base table, non-unique secondary index subtable experience a somewhat similar degree of skewing as the base table does, mitigated or altered possibly by how the index column value combination is distributed over the part of the base table that resides in a particular AMP. As a first technical prerequisite, we need to have statistics collected over the NUSI columns much more than we do for a unique secondary index, because the optimizer can become biased towards NUSI renunciation if it has to rely on a rough estimate of the column distribution in the absence of statistics. Second, once equipped with an unbiased picture of the NUSI content, the optimizer decides in favor of the NUSI if, over and about, the percentage of rows that qualifies for the query is 1 divided by the average rows per data block. Note that this threshold closely corresponds to the situation where every block contains one relevant row, so that we might as well decide to scan them all. If all data blocks have to be accessed, the optimizer decides for a full table scan. We can expect to see both full coverage with index-only access and partial coverage with NUSI in place, but the chance of being used is much smaller in a partial coverage scenario for a NUSI. Regarding the usage considerations, the picture for a non-unique secondary index is much less clear-cut than it was for the unique secondary index before. Why is this? First, the NUSI can cover equality constraints, inequality constraints, as well as conditions leading to range scans. Even the like operator does not prevent the non-unique secondary index usage per se. Under ideal conditions, the column combination used for row qualification matches the indexed columns of the NUSI for a NUSI binary search. Then the row hash of the qualifying rows is equal to the row hash of the indexed NUSI columns, and this is a clear indication for the usage of the NUSI. But we have to be complete in terms of the NUSI for it to be used. So if the indexed columns are A and B, but only column A is used for row qualification, the NUSI will not be used. If the index column is A, but columns A and B are used for row qualification, then we have the situation that the row hash of the base table, column A, is equal to the row hash of the NUSI column A, and this is used to traverse the NUSI, and the row qualification on the column B is then done as a residual condition. We can draw the conclusion for the aforementioned pattern that multi-column NUSI are not too useful. Rather, we recommend to split indexing into several single-column NUSI instead. A special feature of the non-unique secondary index is that if the index column is A and the qualification of rows is done with a like statement, for example, where A like text percentage, a full table scan on the NUSI subtable may occur. NUSI usage is more likely if the index is covering. A NUSI index is even suitable for aggregation, so that our count of base table rows can run over a NUSI subtable instead. Coverage is also given if no column is referenced, such as in a select count star from query. With a little intuition, you may already see why this is allowed for. The NUSI subtable holds the row ID or IDs of the base table per NUSI combination. Counting involves nothing but recognizing the presence of a row. We already have a presence of the row manifest in the NUSI subtable. Calculating any other aggregate here, where we have to perform a calculation with the row content, cannot be fulfilled by just walking over the row IDs. Partially covering NUSI may be used if the amount of qualifying rows is small, and therefore the required lookup of base table rows via row ID is limited. Here, the columns of the query constraint have to be available in the NUSI. Note that this holds true for an optimizer that bases its decisions on recent statistics. Beware not to trap yourself when you are about to index on character fields. Indexed character columns have to be defined not case-specific, as the NUSI stores them always in uppercase, and coverage will therefore not be given for a case-specific column. Nevertheless, coverage can be reached by using the uppercase function in the SQL. A word of caution here, as we just recommended using a function on a column in the context of indexing. Apart from upper, like, and only few others, function-based reference on a base table column turns the optimizer away from considering an index. Given we have a NUSI over the column B, a binary search in the NUSI data blocks occurs for fully covering data requests such as select column B from our table where column B equal to X, as well as for partially covering ones like the following: select column A, comma, column B from the table where column B equal to X. A sequential search associated with a full table scan of a NUSI data block will occur whenever we select in the following way: select column B, count star from the table group by 1. A third possibility, a range full table scan in data blocks for value ordered NUSI, can also take place. We will show you some real-world explain plan pieces for each of these three possibilities. Here's an example of a binary search. We defined a table called NUSI demo, of which a column is called my text, and we query over this my text column with the condition of it being equal to RO. Now, this table contains thousands and thousands of rows with all kinds of combinations, one of which, and a small enough fraction of which, is this RO. In the middle part of the slide, we highlighted in yellow the original explain plan part that reveals what happens when we start this query. We have a non-unique secondary index defined over my text, and the optimizer recognizes it and uses it, as is revealed by the relevant phrase of by way of index, #8. With no residual conditions reveals there are no other conditions, there's nothing more to evaluate over the base table. So what happens in the background? The row hash over the text RO is calculated. It is sent together with the column value RO to all amps. Each amp can retrieve the qualifying index row by a binary search. In this example, the index is clearly covering, and no lookup of the base table row is needed. We have altered the query a little for the next example. First, by including a PK column, imagine this as a primary key, as a part of the primary key, and we change the where condition so that we use a like RO% instead of an equal to RO. The explain plan that was created out of this query reveals that the index over my text is still used, only in a slightly different way now. As we are not so specific about what we are looking for, not equal to RO, but anything with RO, the index is traversed in a full table scan mode, as we can see from the phrase by way of traversal of index 8. Index 8 is our my text index again. So the NUSI is full table scanned, applying the condition RO% on the NUSI column value, and the NUSI row IDs are then put into the spool. As we are not done with simply having a look at my text, but we need PK, and PK is not part of the non-unique secondary index, we need to go back to the base table, having the row IDs that we are looking for from the index table, and take the information we need from the base table. Note that if we alter the where condition another time by making it a substring over my text equal to RO, the non-unique secondary index will not be used anymore, as it has been mentioned before that with only few exceptions, function-based lookups do not happen. taking away the where condition and replacing it with a group by constraint, so that we effectively group over my text, still lets the optimizer use the index, but this time again in a full table scan mode. We see by way of traversal of index again in the explain plan. Even with aggregation or any indiscriminate search over an indexed column, the non-unique secondary index may still be used. Whenever we decide to order non-unique secondary indexes by the values of the columns we index over, the row pointer array in the NUSI blocks carries integer representations of these ordered values instead of the row hashes of the rows. A classical example for a data type that fits into such a 4-byte integer is a date, because dates are stored as integer values internally anyway. Before the introduction of partitioning, value-ordered NUSIs were the only option to establish fast range scans over dates. Value ordering an index over one date is an alternative to partitioning the base table by that date whenever you want to avoid restructuring the entire table and instead outsource this feature to an object you can remove quickly, while removing partition is more costly, for example by creating a copy of the base table and shuffle the entire table content to the copy. Rather than partitioning the base table, you can as well outsource it to a join index over the table. Establishing value ordering alters the content of the master index and the cylinder index as well. Instead of the row hash values, the integer representations of the ordered column values are stored now. We can then locate the relevant blocks via, for example, the date values. Here's an example of a value-ordered non-unique secondary index we created over myDate, ordered by the values of start date. When we select myText from the NUSI table, where myDate between a particular range, for example 1/4 here, what we see in the explain plan is a traversal of the index we created. So it's again a full table scan mode, but it's a range full table scan, as is revealed by the text of with a range constraint. So that the NUSI table in this example is fully scanned, but only over a limited range. There are some limitations, as well as some degree of freedom that we have to take into account for an overall indexing strategy. One limitation is that non-unique secondary indexing is not open to stacking, so no other index objects can be placed on top of a NUSI. We are nevertheless free to combine one NUSI with another, and as a special issue with NUSI, we can achieve a live combination of several NUSI in the form of a bitmap. Let us explore this with some examples. Going back to the NUSI demo table and the myText non-unique secondary index, we now alter the select statement a little by making it two conditions combined with an OR operator. So we look for myText equal to ROA or ROB. The sequence of events that occur in the background and are revealed by the optimizer is the following. The row hash over RO is calculated, sent together with the value to all amps. Each amp can retrieve the qualifying index row doing a binary search. We can see that there's a binary search from the by way of index phrase of the original optimizer text. Then, as the index is covering, no lookup of the base table is necessary, but we still have a second condition to work over, that is myText being equal to ROB. And this is the second part of the optimizer text we copied here. This is a second run over the index, a binary search again, no full table scan. The result of both these operations is a set of row IDs of the base table. This set of row IDs is finally combined before we go over to the base table, which we do not have to do in this case. Let us explore what happens if we combine where conditions over columns with an OR statement. In the example mentioned, we look for rows qualifying either myText1 equal to RO or myText2 equal to RO. myText1 is indexed, but myText2 not. In this case, as you can see by the relevant phrase of all row scan from the optimizer citation, we are not able to use the NUSI over myText anymore. Why is that the case? Because the second condition demands a full table scan over the base table anyway, it is not efficient to work with the index over myText1 and do as a second step what we could do immediately, namely the inevitable full table scan. Therefore, the optimizer decides against the use of this index and performs a full table scan, evaluating both conditions over the base table. If both text fields were indexed, the OR condition forced the creation of two row ID lists from the two indexes, plus a sorting over these two lists in spool to arrive at a net list of row IDs before turning to the base table with this one net list. This is a costly endeavor relative to a full table scan. This has to be taken into account apart from the question of selectivity. Our NUSI demo table has two text fields called myText1 and myText2. We introduce an index, a non-unique secondary index, over both myText1 and myText2 now. The SQL statement imposes the condition that myText1 equal to RO and myText2 be equal to RO as well. We see clearly that we are back to index usage. The row hash over RO is calculated, sent together with the column value of RO to all amps. Each amp can retrieve the qualifying index row via a binary search, but the second index over myText2, although we have just created it, is not used. The second condition is considered a residual condition that we will apply on the base table once we have retrieved the relevant row IDs from our first NUSI. This example reveals an important finding. The optimizer will not always use each of several indexes for conditions combined with the AND operation, but only the one index with the highest selectivity, given that there is high selectivity at least on one side. If neither of the indexes is strongly selective in isolation, but a strongly selective condition emerges out of a combination of NUSI, the optimizer will employ the bit mapping technique. But of that later. When we depart from equality conditions alone and introduce a not equal to RO constraint on myText1, selectivity relationships flip side. The equality condition over myText2 is now relatively more selective. We see that index usage versus non-usage flip sides accordingly. Now it is the index over myText2 that is used, by way of index number 12 reveals it, and the first condition becomes the residual condition to be applied over the base table. With the following, you might see a little clearer how the optimizer, over and about, arrives at the conclusion that we are in a high or low selectivity situation and whether index usage pays off. The upper threshold for NUSI usage, instead of full table scan, can be determined as 1 divided by the number of rows per average data block size % of the rows qualified. Data block sizes are taken as an average here because they are not fixed. They can vary within a band of sizes. If a table row is defined such that on average 50 rows fit into one block, then the threshold for index usage for that table is 1 divided by 50, which is 2%. So any query over an indexed row that is selective enough such that 2% or less of the data of the base table row qualify, other things equal, the index will be considered. With 500 rows per average data block size, the threshold becomes 1 divided by 500, which is 0.2%. At the very extreme, when one block stores all the rows of a table, a NUSI will never be considered, because a full table scan is always the more efficient approach. At the other, more hypothetical extreme, one block can digest no more than one row on average, then the NUSI will always be considered as 1 divided by 1 becomes 100%. An increase in the size of a row leads to a decrease in the number of rows per average data block size, which drives the threshold up. The NUSI usage becomes more likely, other things equal, with larger rows. Pumping up character field length is one such example of an increase in the storage space needed for every row. It follows that the widespread rule of thumb of a 10% of rows selected threshold is more of a folktale than an accurate measure. In order for the threshold condition to work out well, in reality, the optimizer has to have a true picture of the data in the form of statistics. In the absence of statistics, the optimizer samples on its own and arrives at a conclusion derived from the sample of rows. But the fundamental mechanics just presented to you by the threshold calculation always hold true. A special kind of live selectivity that we can achieve with non-unique secondary indexes is the NUSI bitmap. How is it defined? When we have several non-unique secondary indexes that are weakly selective each, but that, by the way they are combined, are strongly selective together, this is the prerequisite for a NUSI bitmapping. It is implemented in the following way. The row IDs of the 2 or more NUSI indexes that are inputs to bitmapping are combined, and the intersect list is then used to look up the base table. Such a bitmap is built on every AMP. Note that this is a special feature that is not a standard process of how row ID lists are compared and operated. We can achieve this situation whenever we combine, for example, 2 weakly selective non-unique secondary indexes with AND condition. As an example for the strong selectivity in combination, consider the following. Imagine you have an index over the education level of your clients. You have millions of clients and only 6 or 7 education levels from no schooling or only primary school up to university degree. And on the other hand, you have a net asset value categorization from no to low assets up to wealthy. Now, with millions of clients, each of these classifications alone can apply for hundreds of thousands. But the combination, especially when we look for rather rare combinations, can be highly selective. Imagine a super rich illiterate or a PhD holder that is poor. When 2 indexed columns are combined with an AND condition, both sides form a representation of zeros and ones for the fulfillment of the individual index condition. The bitmap result is then the list of rows that have ones on each individual index. Bitmapping is not limited to 2 indexes. As this example indicates, it might well be that the combined selectivity of 3 or more columns is high when each of them alone is not. Looking at this example, we see that with 3 conditions over column 1, 2 and 3, condition number 1 is fulfilled by 50% of the rows, number 2 even less selective by 75%, and 3 a bit more selective by 20%, but the combined condition is only fulfilled by 5% of all rows. And this is a hot candidate for bitmapping. The last kind of index we wish to discuss in this webinar is the single table join index. Do not be misguided by the name. Although we do not create joins with other tables, the notion of single table join index is used in all documentations and references. This is due to the fact that
The single table join index is a special case of the multi-table join index, only on one table alone. From its general design features, it has more in common with a separate base table than the other indexes we presented so far. The range of functionalities goes beyond what can be achieved with a secondary index. Furthermore, it is the only index that can be defined in a unique or non-unique fashion without having to create a separate kind of object. When do we recommend a single table join index? First, if you are in need for an alternative primary index for a particular base table. Typically for joining or for lookups, you might work in a data warehouse where you have purely technical keys that serve you well in terms of data warehousing tasks, but do not serve your customers well in terms of reporting. They have alternative keys for the same entities they use a lot. In this case, consider creating single table join indexes with primary or even unique primary indexes over these alternative keys. Second, if what is interesting about a table is not the whole set of columns, but typically only a small subset of columns, and if this small subset is constant over time and over various reports, consider creating a single table join index that holds exactly this small subset, even though you work with the same primary indexes as you use for defining the table. Third, if you wish to establish value ordering and cannot change the base table, for example, you cannot introduce partitioning, or you shall not introduce this kind of partitioning in order to work with range scans a lot, define a single table join index that holds ready for you the kind of value ordering you need. For every row of the base table to reappear in the single table join index, we include the column values we indexed upon, optionally also the row ID of that very base table row. This is a first difference in purpose to the other indexes discussed so far. A single table join index is not primarily designed to alternatively access the base table rows via a pointer to the row IDs and only optionally cover a query alone, but first and foremost to cover queries on a regular basis with no descending to the base table row. The single table join index is the only kind discussed so far where we explicitly define a new primary index for the selected part of a base table. Therefore, we have the same row pointer array sorting and AMP distribution pattern like for a primary index. The single table join index rows are distributed by the primary index row hash of whatever was said to be the primary index of it. A good distribution is a matter of a wise primary index choice, much like it is for a base table. If the primary index was said to be unique, general Teradata design features prevent any skewing. Non-uniqueness of the primary index opens up the possibility for skewing. Again, much like for a base table. With a single table join index, there is no coverage for indiscriminate select star from queries, even in the peculiar event that your single table join index is a complete replication of the entire set of base table columns, only with a different primary index. Full coverage will be achieved if queries match the original purpose behind the creation of the single table join index perfectly. That is, when the select line and the column set of the single table join index are identical. Partial coverage is also possible with single table join indexes under the following conditions. First, query and single table join index columns do not perfectly match, but the row ID of the base table is part of the single table join index column set. We saw this in the code example before. Second, the single table join index repeats all the base table unique primary index columns of the base table in its select line. Third, the single table join index at least repeats all the columns of a unique secondary index defined on the base table. The access behavior of single table join indexes can be compared to that of a unique secondary index in that we either have a hashed access with a binary search on the primary index or a full table scan over the single table join index table. This variety of access patterns allows us to use the single table join index as an alternative version of a base table for tables that are accessed in various ways, some of which are unrelated to the primary index of the base table for good reasons. If alternative joins happen a lot, consider manifesting these join options in the form of a single table join index. Data blocks can be sorted by the row ID of the primary index, as well as by 4-byte integers for value ordering. Regarding the combination possibilities that we have with single table join indexes, first, we can use several single table join indexes together in one query. The optimizer recognizes the existence of each of them and may use them all. But we cannot stack them. But what we can do is stack other indexes on top of a single table join index, as long as it is a non-unique secondary index kind, but not a unique one. We can also partition existing single table join indexes to enable range scans. The single table join index can be used in various ways. The set of prerequisites is relatively small. Depending on whether we hit the primary index definition of the single table join index by the column combination we use for row qualification, we can first achieve even a unique primary index access if we happen to have a unique primary index defined for the single table join index, but we can get the optimizer to using the single table join index as well if we query in a way that does not match the single table join index, but the optimizer comes to the conclusion that it is comparatively cheaper in terms of I/O to use the join index instead of the base table for executing the query. Thank you for listening to our webinar. I hope that we contributed a lot to giving you a broader and deeper understanding of what indexing is all about in Teradata. If you liked our webinar and would like to see more webinars on this or other topics, let us know. Leave us a short reply on our Facebook page. If you are not already a subscriber, we invite you to subscribe to teradatapro.com, where we share our knowledge with you in many articles and practical code examples. Let your coworkers and friends interested in Teradata know we are out there. We wish you great success with indexing.